batteries, chargers, fire risk, and the standards that are helping an entire global industry work towards safety. It is a very big topic, this topic of e-mobility. And fortunately, we have two very big minds in the field to tell us about it here today. Our guest today, Ben Gaudet, Manager R&D right here at UL Solutions. Ben has about a little over 7 years of setting things on fire here at the company. And Alex Schraber, Senior Manager R&D, also with UL Solutions. She has been setting things on fire here for just over 8 years. Now, we have a lot to talk about today here, like we just said. But before we dive in, guys, tell us just a little bit about yourselves. Alex, you deserve better than just setting things on fire here at UL Solutions. So please tell us a little more about yourself here and what you do with the company and your role.
Sure. So as an R&D group, we are trying to always be mindful of where hazards are going, where emerging hazards are coming from, and how they affect life safety and property safety. So my background is in mechanical engineering and fire protection engineering. And what excites me about this role at R&D and at UL Solutions is the ability to take those topics we learned about in school and all those different frameworks for looking at hazards and then applying them to practical real-world problems.
We have seen some of the real world problems that you and your team have tackled. We're going to be looking at some of that later here. And Ben, tell us a little bit about yourself before we get started.
Sure. So, like Alex, also background in mechanical engineering and fire protection engineering. And that from Worcester Polytechnic Institute, originally from Massachusetts. So, as Alex was mentioning, our job and our role here allows us to look at a lot of different problems and all aspects of it, from the start to the finish, and try to understand the right solutions. So it's exciting and it's always a lot of fun.
All right, well, let's start here broadly with e-mobility. Ben, first question is for you. First of all, what exactly is e-mobility? And then are there any various subsets of e-mobility?
Sure. So generally speaking, e-mobility is, well, mobility that's powered by electrical power. So it's a broad category, and it can include things like electric vehicles, or smaller devices like e-scooters, e-mopeds, motorcycles. So it's generally the broader category. And a smaller subcategory of e-mobility is something called micromobility. So these are devices that are kind of the e-scooter, the e-moped type of device that tend to be smaller, and they tend to also not be used on the roads. So I guess another differentiating factor between the broader e-mobility category and micromobility is that e-mobility devices can be larger. They are usually road legal. Micromobility devices are not used on the roads and tend to be a little bit slower. Oftentimes, one of the differentiating factors is that speed. So larger e-mobility devices are maybe 35 miles per hour and up, whereas micromobility devices are usually 28 miles per hour or lower.
Okay. Next question for Alex. All right, this is a pretty growing field. It's growing pretty quickly, but how quickly is it growing? And with that, we get some more safety risks. So what are some of the more common incidents that are commonly associated with this technology, whether it's in like the broader sort of EV vehicles, the 28 miles or 35 miles an hour fast out in the roads, or some of the smaller micro-mobility vehicles? Where do we see some of these issues?
Sure. As adoption of these technologies has really taken off in the last several years, we see a natural increase in the number of incidents. So as you have more of these products on the road and they're being more and more widely used by consumers, there's a natural increase just in the number of incidents based on the number of products that are out there. In the electric vehicle space, a lot of the incidents involving fire or gas release hazards come following a collision. But in the micromobility space, there's a number of other ways that these hazards develop and patterns we see as it relates to failures during charging, failures during storage, oftentimes failures during repair. So either user modification of products or someone who says, hey, my battery's having an incident, and someone tries to go into that pack and repair it. We see incidents develop in those scenarios as well. Depending where the failure occurs or where the product is when it fails, really contributes to the overall consequence and severity of the incident. So one of the more concerning patterns is if the failure happens while someone's charging their scooter overnight at the front door of their residence. So the hazard is developing in the evacuation path, potentially blocking their ability to evacuate if an incident occurs. So that's one of the patterns that we've observed in the field incidents that we've been tracking, and it's one of the concerning patterns.
So if somebody has, say, like an e-scooter and they're charging it in their home, what, let's get a little focused, a little specific here. Hang on, what's one of the more likely scenarios that we're likely to see with the battery in that scooter? Is it going to overheat because it's charged too long? Is it because the parts aren't certified? Does the battery actually explode? Is it just going to get really, really hot and cause problems that way? What specifically are we looking at when somebody has a vehicle like that plugged in, charging in their home? What's likely to fail, if it's going to?
Sure. So the failure can occur in a few different ways. One of the patterns is if you have an incompatible charger with the battery that's being charged, or the battery pack doesn't have the protective circuitry and control system, or that's been damaged in some way. The charger can overcharge the battery. And then the battery itself, the cells, can either overheat and have failure that way, or you can have an internal short circuit within the battery cells, which results in a failure mode called thermal runaway, where you have a direct short between the positive and negative terminals of the battery inside the cell, and then you have enough current pass through that the heat can't dissipate fast enough, and that triggers the chemical reactions in the cell that could result in flammable gas release, toxic gas release, and potentially fire from that. If that gas accumulates within a residence or another structure or area, that's when you could have an explosion hazard potentially develop.
Okay, you just mentioned thermal runaway. Ben, next question is for you here. What precisely is thermal runaway? I mean, people like me would think, oh, it's just a fire. Why don't you call it fire? Well, no, there's more to it than that. So what exactly is thermal runaway, and what does it look like when thermal runaway happens inside one of these battery enclosure systems?
So generally speaking, thermal runaway actually isn't something that's only limited to a lithium-ion battery. The idea of it's been around in fire protection engineering for a while, and originally it was part of a phenomenon that you'd see in large piles of combustible materials that are well insulated. And basically the idea is that if you have some chemical reaction inside of your system that produces heat, and that heat is accumulated faster than the system's able to dissipate it, then as you would expect, that the temperature of that system starts to gradually increase. And eventually that rate of increase gets faster and faster until a point where it increases at an extremely rapid rate, and that's when we get thermal runaway. So sometimes in the cases of, as I mentioned, those piles of combustible materials, like even wood chips, that can lead to a fire. I mean, a very small version of that can even be seen if you've ever reached into a hot mulch pile, right? You feel the heat that's accumulating inside of that pile of material. In a battery, it's the same physics, only the chemical reactions are happening inside of the cell and result from this damage to the cell. And as Alex was mentioning, this short between the anode and cathode of the cell. So when this happens, the temperature of the cell increases extremely rapidly, sometimes to temperatures of several hundred degrees or even a little over 1,000 degrees Celsius. And flammable gases are released. And just because of the sheer amount of heat that's there, often you have a fire that results too.
Okay, like how quickly can you go from safe to 1,000 degrees Celsius? Like how quickly can that happen in some of these products?
So it's a good question. So as far as the event of thermal runaway itself, that happens very rapidly, usually within a matter of seconds or even under a second, a fraction of a second. But the things that can lead up to thermal runaway, for example, the abuse, the damage, the increase in temperature, those can happen more gradually. But what makes some of these incidents so dangerous is that a lot of the, say, gradual internal heating or that damage cannot be is not visually seen by folks that are around the product. It's not very obvious. So when thermal runaway does happen very rapidly, sometimes it can be seen as almost without warning.
Okay, so very gradually and then very suddenly. It might happen like that on occasion. Okay,
Right.
definitely be very, very scary right there. All right, Alex, next one's for you. What do the hazards look like in some of these different e-mobility products? Now, we were just talking about scooters there, but e-mobility covers a lot, as you guys have both just said. So what are some other risks that we can see specifically in some other e-mobility products that you and your team are typically looking out for or like have worked on?
Yeah, so to add also onto what Ben was sharing, that first thermal runaway within a single cell or within the first few cells can happen suddenly, and the overall severity and how that will develop in different products is going to depend on the overall design and construction of that product. So some products may have that failure progress very rapidly through the full battery pack. So if, for example, there is a lack of protective circuitry in a scooter, let's say, and the full battery pack is able to overcharge at once, you'll have a very severe failure pretty rapidly propagate through all of the cells in that pack. Now, if the failure is initiated by a manufacturing defect or something that may only affect a couple of cells, if the pack is well insulated with pretty robust construction, that may progress very gradually. So depending on the product's design and the different construction features of it, you may see those different rates and different severity come from that. As it relates to electric vehicles, oftentimes there's pretty robust construction, especially to pass the crash tests and all these other things that road vehicles are expected to withstand. So often there's a lot of insulation that will help slow down some of the initial development of that event. In something like micromobility and these smaller products, a lot of the event development is going to depend on the enclosure design and the pack design. So how robust the enclosure is will direct gas venting in a certain direction and contribute to the overall impact that has on the product. So you can see differences between plastic and metal enclosures, for example, and then the overall event magnitude can be impacted also by just the overall size of the product.
Okay. Clearly, there are a lot of variables here and a lot of different products. And UL Standards and Engagement recently published two standards in this general area. UL 1487, that's the standard for battery containment enclosures, and UL 4900, that's the standard for micromobility charging equipment. Both were in February earlier this year. So, Ben, this one's for you. Could you tell us a little more about each one of these standards and how they apply specifically to e-mobility safety?
Sure. So UL 4900 is for micromobility charging equipment, and the purpose of that standard is to fit into the ecosystem of UL listed products within the micromobility and e-mobility space. And it's designed for products that are meant to act as charging stations or charging devices for micromobility usually. So if you've ever seen like those Divvy bike stations that are around larger cities or other, larger micromobility charging stations, that's one of the, form factors that a micromobility charging device could take. It could also be a device where you slide batteries into a slot or a cubby. And generally speaking, the focus of that standard is the quality of the electronics in the device and the fire prevention. 1487 is kind of a complement to 4900 in terms of how the hazard of fire safety or how fire safety is being approached, whereas 4900 is more of a reactionary standard. So 1487 is more of a reactionary standard. So UL 1487 is the standard for battery containment enclosures, and it's designed for products that are intended to contain and mitigate thermal runaway of a variety of lithium-ion battery products, not necessarily just micromobility, but that particular space is an area where this type of product is likely going to be used.
Okay, so 1487, you called that reactive. That's basically because in case there is thermal runaway, then this is how it's going to respond. So if there is a reaction, then you can try to contain it and mitigate the risk there. Whereas 4900 is about, this is where people are likely going to be charging batteries, so let's just prevent it or reduce the risk of it happening before there is a thermal runaway. Correct?
Right. So in 4900, it's part of the language of that standard is that it's meant to be used with UL listed devices. So again, it all works together in that ecosystem. Whereas something like 1487 is intended for when you don't necessarily know what's going to be going inside of that storage container. So some of the applications may be cabinets where you're storing batteries between their use, for example, for tools or for e-mobility batteries or even the device itself. Another potential application is for overhaul for the fire service. So if devices need to be safely contained while the scene is being assessed and overhauled. And it's very possible that the batteries being pulled out of the fire scene are damaged, and the likelihood of thermal runaway is high, then 1487 based containers are a potential way to safely keep those batteries stored while the rest of the processes are going on.
That is very interesting. A lot of people, especially people living in more urban areas, definitely have an interest in this because some of those like public charging stations that you mentioned earlier, a lot of reports say those are growing in popularity. We're going to see more and more of those due to a shift in how people actually want to maneuver themselves around bigger cities. So shared type of like e-micromobility vehicles, those are going to be big. So people are going to be seeing more and more of these stations likely around their bigger city neighborhoods, and knowing that there's the science, the safety science behind those to make them safer to use and less likely to cause an issue will definitely give people some peace of mind on that. So thank you for that. Next one, we also have UL 2596. That is the test method for thermal and mechanical performance of battery enclosure materials. This is also the torch and grit one, the torch and grit, right?
Right.
All right, I got that one right. That's great. All right, so whoever wants to answer this one can. What is 2596 and how does it play specifically into the safety of e-mobility, specifically to electric vehicles? Tell us about the torch and grit method.
Sure. So I can take that one. So as you mentioned, 2596 is mostly in the e-mobility space, specifically this time electric vehicles, although there's no reason it can't also be used in other spaces. Whereas 1487 and 4900 tend to be applied mostly to the micromobility space. Another differentiating factor is 4900 and 1487 are what we call end product standards, where you're testing an entire system as a whole, and there's a whole variety of tests and assessments involved in that. Whereas UL 2596 is a materials level test. So the point of 2596 is to assess for resilience against thermal runaway. So there are two tests within 2596. One of them is the torch and grit, as you mentioned, and the other is something called battery enclosure thermal runaway, or BETR. And both of them are designed for screening of materials for applications typically in EV battery pack enclosures. So there's also potential applications for the separated materials that are between cells that, as Alex kind of mentioned earlier, can help prevent that propagation of thermal runaway. And there's also potential for applications in the micromobility or other battery-powered product spaces where there's a need to either contain thermal runaway or to reduce the speed at which the event gets worse. So the way those methods work is that they apply a standardized exposure that's representative of the severity of thermal runaway. And because that exposure is the same every time, manufacturers can come with different material formulations, thicknesses, and they can essentially rank them by looking at things like time to failure, heat transfer, and breach.
Okay, and you said this is for the torch and grit, not the better one. This is for screening the materials. So like before the battery enclosure is actually built, you want to test the materials out of which it will be built to see if those are the best materials, right? Okay, hey, John, that's John Wisniewski, everyone, our producer here. He has some video of this, of you guys actually applying the test. John, are you able to bring that video up? And we could have our experts here actually speak to it a little bit. And people who are watching this right now, not just listening, this is what our UL Solutions engineers do a lot of every day. Guys, this is the torch and grit method. And Ben, Alex, why don't you take it away? What exactly are we looking at here?
So what you're seeing there is the front end of the torch applying about a 3 kilowatt flame to a test sample. And the way the torch and grit method works is that it's a cycling between a flame only and a flaming grit blast. So down the center of a torch is essentially a compressed air channel that ejects particulate at the sample. And it does this in a cyclical pattern between flame only and this flame with this abrasive blast of particulate. And the idea is that you can go through a series of cycles until a material fails. So if you run 10 materials, each material may have a slightly different number of cycles to failure. So it creates a nice and simple way of ranking materials A, B, C, and so on, and even thicknesses or different potential variations in geometry. So what we're seeing here is the front end of that apparatus applying the flame to the material sample.
It sounds kind of like you took a sophisticated sandblaster and a blowtorch and combined them into one tool here.
Exactly. Like I said, what we do here is fun.
Wow, that looks really neat right there. And that material that you're currently testing right there, that is just one example. You could get all sorts of different thicknesses, and like you said, all sorts of different materials, see how well it's going to stand up to whatever series of cycles and sequences you put it through, and then that would then help manufacturers determine which materials to use to help reduce risk in their enclosures, right?
Right. And then something
Okay.
like this fit along with the variety of other considerations that manufacturers have, from sustainability to cost effectiveness to weight, right? And this helps make sure that fire safety, particularly fire safety in relation to thermal runaway, is also accounted for.
Wow. That is really neat stuff. Hang on, like momentary aside here, is doing stuff like this one reason why you guys get into this line of work? I mean, here in marketing, we don't get to play with stuff like that at all, but this looks
Yeah,
like it's fun.
it is. Like I said, we get to bring projects like this from the ground up, from inception through testing, and then eventually, expanding it out into the world. And it's satisfying to see that. But setting stuff on
That's very
fire is also fun in its own right.
okay. This is some fascinating stuff here. This material is evolving very quickly, economically and whatnot. What challenges are you likely to start seeing, do you think, in like the next 5 years as e-mobility continues to advance? Like, what new challenges do you think are going to start walking through like the laboratory doors? What do we have to look forward to?
Good question. I guess I'll start. So, I mean, as one trend we see with energy systems is that their density is increasing, right? So, and with any engineered system, when you have energy in some place, it's going to try and find ways to get out, typically. So as energy density of batteries increases, it's possible that the resulting failures can be more energetic. But at the same time, there's also trends towards battery technologies that are more stable, for example, solid state batteries. So there is potentially a trade-off in the technologies between the increase in the potential hazard and the decrease in potential hazard.
Okay. What exactly is a solid state battery? I mean, we don't have forever, but what exactly is a solid state battery, and how is it different from a lithium ion battery? Lithium ion battery.
So, I mean, honestly, I'm not an expert in that particular, engineering science, so I don't want to pretend to give, the full
All right.
answer. But generally speaking, one of the main differences is that the electrolyte within the battery is, instead of being a liquid, which is the case in lithium-ion batteries, it's a solid electrolyte. So, in ways that I'm not entirely privy to, because again, I'm a mechanical engineer, so I prefer to stay in my swim lane, right? But the transition from the liquid electrolyte to the solid electrolyte does provide benefits and stability.
A lot more research to be done there as well, I'm sure. Alex, what do you think we're going to be looking at risk-wise or research-wise the next couple of years in your field?
So I expect to be surprised by batteries in this industry in one way or another. I think that's been one of the consistent through lines of the last several years, is that when I think I know what designs are going to look like, something creative and interesting comes through the doors. Something that I'm excited about, I think, is as we've seen safety and fire safety become an increasingly attentive part of the design cycle and the hazard awareness, both on the manufacturing side and the end user side. So I think as we see this increased consideration for fire safety, both in product design and the implementation considerations, like with storage cabinets like the UL 1487 products, I think we're seeing fire safety come earlier in the design process and not just right at the end. So for me, that's exciting to see what innovations will come with that. So as Ben said, there's always a pressure towards increased energy density, but the way people are achieving that with either chemistry variations, solid state batteries, or just different materials in the packs in general, is an exciting place for innovation. And I think we're seeing safety increasingly at the forefront there, which I think is exciting. As much as Ben and I enjoy an exciting fire test, I think we do also welcome some of the more boring fire tests, because that means that product safety is being pretty successful.
Excellent. All right. We're looking forward to having you guys back on again later as the field continues to evolve right there. Thank you very much for joining us today. Really appreciate your time.
Thank you.
Thank you.
And thank you, everyone, for joining us. There is still a lot more to come on the Code Authority. You can check out our website at ul.com/the Code Authority. There's a newsletter, a whole community of inspectors, scientists, engineers, innovators, and people who are really just plain curious. And there's a lot more episodes, too. You can find us on YouTube, LinkedIn, and Spotify. That is it for now. We'll see you back here again later. This is the Code Authority.